Alright folks, we're going to be looking at Pythagoras' theorem in 3 dimensions. I'm going to assume that you've remembered or looked up how to do it in 2 dimensions already, so we're going to crack straight on and just apply it in 3D. So we've got a cuboid here, A, B, C, D, E, F, G, H. Notice you can't see F because it's hidden around the back in this corner here. We're going to find the lengths AC and AG to show you how this works in 3D. Now actually the trick with this is to forget that it's 3D altogether and just make it 2D and make it easy. If we clock on the length AC, it's across the top plane here of this cuboid, and in fact if we take off the points A, D and C from here and look at it at a different angle, we can clearly see that on a cuboid this would be a right angle, which means that this is a right angled triangle. Okay, ADC. Now we have some of these lengths given to us. We already know how far apart D and C are because that's the 15 meters there. We also already know how far apart A and D are because that's the width across here, that's 7 meters. So in fact we're just finding a hypotenuse using everyday normal Pythagoras. So that's 15 squared and 7 squared rooted, which your calculator will tell you is root 15 squared and 7 squared is roughly 16.6 meters to 3SF. Okay, and that's it. You've done Pythagoras before, it's very straightforward in that situation. AG is a little bit trickier because AG is the diagonal all the way from here to here. Now the right angled triangle that would be part of is actually got that and that in. So that would actually be the triangle ACG. Which is something like this shape, and this is just a sketch of course, with the right angle at C. Now we know the height GC, that's the 3 meters given here. The length AC we know because we've worked it out, it's roughly 16.6 meters. We'll come back to that, there's a little neat trick in a second. So this, simple Pythagoras again it turns out, it's a 2D flat triangle, no bother at all, is the square root of 3 squared plus 16.6 squared. Now, think about where this 16.6 came from. It came from over here, where in fact it was the square root of this. So when we square this back up, we're going to get 15 squared and 7 squared, because that's where it came from. So a more accurate way of writing this would be the square root of 3 squared and 15 squared and 17 squared. And in fact, this is because we are actually now moving in 3 dimensions. We're moving xward, zward and yward in this motion, which means you need 3 dimensions to work with, which is why we've got 3 things squared and added. Pythagoras, it turns out, works really simply in more dimensions. You just add on the next dimension squared, except for one special case for those who want to go into some weird stuff. So in 3D it's actually no trickier, it's just rather than a squared plus b squared is c squared, it's a squared plus b squared plus c squared is d squared. And more generally we do this as displacement squared is the coordinates as we need them in the dimensions squared. So getting back to what this actually is, this is root 3 squared plus 15 squared plus 17, that's a 7, that's a 7, that's a 7, this should clearly just say 7 here, apologies for that. 7 squared is roughly 16.8 meters, so only slightly longer than the other diagonal. So thinking about this property and how we can use it straightforwardly in all problems, we've seen coordinate distance before with our 2-dimensional Pythagoras. Here we've got 3 values in our coordinates, which means these must be 3D coordinates. So how far apart are we moving in the x direction? Well, between 2 and 8, that is 6 apart. Between 5 and -2, values are 7 apart. And between -1 and 3, those are 4 apart. Now we're going to square these, so the negatives all disappear anyway, and because we're talking about distance, not displacement, the signs don't even matter. So Pythagoras, square stuff, add stuff, root stuff. That would be the distance. So for those who actually care what the value is, that is roughly 10.0 units between those two coordinates. And this will be true in 3, 4, 5, 100 dimensions. As long as these are all distances, they all square and add the same way. So for GCSE, you need to be able to do this. Whether or not you do the middle step, both methods work. This will get you more accuracy and more efficient. And you need to be able to do this. You don't need to worry about anything high dimensional, that was just if you're interested. For those who are really interested, maybe think about how time fits into these distances with Pythagoras. It's a bit peculiar.